All right, we are going to be starting chapter 11 today, plate tectonics, and we're going to start off with 11.1, Pangaea. So Pangaea, if we all remember, if you've heard any of us teachers talk about it before, Pangaea is that giant landmass that existed around 250 million years ago. Now, one of the fundamental people that gave us the idea about Pangaea existing before we had any of the science that we have today was Alfred Wegener. He was a German scientist. He was the first person that actually suggested the concept or theory of continental drift. Remember, in science, anytime we can't actually see things, we use that term theory. So yes, this is technically called the theory of continental drift. So continental drift, just even look at the name there, continents drifting apart, the idea that the continents move around on Earth's surface. So Alfred Wegener got this idea, and there was quite a few things that led him to believe that this was actually happening. There is Mr. Wegener right there. So matching fossil evidence on different continents. I'm going to show you a map in a little bit what exactly that means. Matching coal beds on different continents. We had matching rock types on different continents. There was mountain belts that lined up. And then finally there was glacial grooves that actually lined up as well on those different continents. When glaciers move across land, they actually scrape the land over the surface, kind of like, imagine dragging something really heavy over maybe a concrete driveway and then scratching that. So they had scratches that lined up on either continent. So here's just kind of a picture showing you some of those things. So you can see, like in North America and Europe, you can see that matching coal beds up there. North America and Africa, matching mountain belts. Same thing in South America and Africa. The matching fossils that we see kind of lined up. And then finally, the one thing that I have not mentioned yet that was actually really important to Wegener was the puzzle-like fit of the continents. I think any of us can agree. Let's imagine, these are puzzle pieces and you cut them out and you fit them together. You can kind of fit it together to make it look like one giant landmass. And I don't think anything is more true than just looking at South America and Africa and then kind of taking those two continents and then putting them together. So using that information, and then now looking, here's some fossil evidence that we have. You can see some different types of fossils. There's some reptiles, there's some ferns. You can see that they line up. If you look specifically at South America and Africa, look at those reptiles that line up. You can also see in southern India, over in Australia, you get those matching fossils that are lining up with each other. Here's just another picture kind of putting it together too, showing you, okay, now if all of these things were connected, you can start to see why you maybe had these reptiles on those different continents. They're not going to swim across the ocean. It's not happening. They don't swim. Same thing with the ferns. So all of these things were kind of like the evidence that gave us the idea of continental drift. So Pangaea, like I said earlier, I think I said 250 million. I was off by 25 million years, which is quite a bit. 225 million years ago, Pangaea, the word that means all Greek. At the time, the sea was actually called Panthalassa, which means all sea, but Pangaea is that giant supercontinent that we believe contained all of Earth's land 225 million years ago. Around 200 million years ago, it started to split up. At the time that it split up in these two kind of giant supercontinents, the northern part was called Laurasia, and then the bottom part was called Gondwana, or it's sometimes called Gondwana land. There's the word theory again. So plate tectonics theory, the theory that Earth's crust is made up of tectonic plates. These plates are in motion. Sometimes they're sliding under each other. Sometimes they're sliding past each other. Sometimes they're actually moving away from each other, but that is what the plate tectonic theory is. Remember, our tectonic plates are made up of Earth's outer surface, the outermost hard part of Earth's surface called the lithosphere. Remember, that is technically the crust and the upper mantle. So there's just a picture of Earth's tectonic plates. Now, this is just one map. You can go on a safari and you're going to find other maps. These are the biggest ones. There's even smaller ones that you can find in different locations. For the most part, obviously, the big ones are going to be the ones we can note. For example, the Pacific plate found underneath the Pacific Ocean, or you can see the Antarctic plate, or the one that we live on, the North American plate. So these are all tectonic plates. They are pieces of the lithosphere. I like to kind of think of them like a hard-boiled egg. So if you go to crack that hard-boiled egg and you got those pieces of the shell, it's still kind of attached to the egg, but they can move around a little bit. That's really what Earth's tectonic plates are doing. They're attached to Earth's surface, but they move around. Like I said, in some places they come together, some places they come apart, and some places they actually slide past each other. probably most famously known in our country would be the plate boundary that is out on the West Coast. I don't think any of us can think of California, think of the West Coast without thinking about earthquakes or even the volcanoes that are located out there. And you can start to see really why that actually occurs. California is located right along the plate boundary, Pacific plate, North American plate. So if those plates are moving, obviously you're going to have earthquake activity.